Hello, YouTube! Today we're going to talk about the actual calculations behind the vocab that we were talking about last time. Um, Little bit weird, just as a heads up, is that the worksheet for this one is pretty much combined with the worksheet for the next one, because this is a little bit too... It felt more useful to have both of the concepts together because that's when they really start to get interesting. Um, so that's why that's organized like that. Ideally today, end of the day, take all that vocab from yesterday and be able to actually model it with math. So instead of just being able to define total distance traveled, displacement, average velocity, and average speed, actually being able to calculate them is the big focus. So if you can do this problem by the end, you're probably in pretty decent shape. We're going to do another problem that people tend to find harder after this, but this is sort of going to be what we're working towards throughout today. So the basic premise is I walk 20 meters forward from my room towards my car. I realize I left my glasses on my desk. Walk 25 meters back. This happens in embarrassingly large amounts of the time. I then walk 40 meters forward towards the car. So what was my total distance traveled? What was my displacement? What was my average speed? And what was my average velocity? And generally speaking, for these, we're really going to want to start by drawing a picture. But we don't actually really know how to do any of this yet. So we're going to start out with the total distance traveled and displacement, come back, do those, and then learn about the other two, come back, do those. So the big thing is that total distance traveled, which I tend to abbreviate as TDT, you could also probably just use D and it would be fine. And the units are meters. This is the sort of nomenclature or way that I tend to communicate variables in these slides. It'll be the variable name, comma, and then the units for the variable in brackets. And I think that's just a me thing, but just so you know, I do that fairly consistently, so that's what that means. So the big thing for total distance traveled is that you're going to... Oh, I don't like the phrasing on ignoring negative movement. I would say ignore any negative, like, in the movement. So what you want to do is just add up all the distances, right? It is the total of all distances traveled. So really all you got to do for that is anytime that you know that someone went a distance, take that, take the number, don't worry about plus, don't worry about minus, don't worry about forward or backwards, just add it in. Displacement a little more complicated in some ways and actually a lot easier in others. There's two main methods of doing it. In either case, its symbol is delta x. X represents position, regardless of whether or not it's in the... Well, for now, x represents position. When we get to two-dimensional, it'll be, okay, well, x in one dimension represents x movement, y represents the other dimension. But for now, x is just position, or in this case, because it's delta, and your displacement is the change in where you are from start to finish, delta x means change in position. Delta meaning position, change in, and that's going to come up a lot throughout the year. So the first way to do it is to take all the distances you went and keep all of the signs. So like if you go 20 forward and then you go 30 backwards, you would include the plus for the 20 and then minus for the 30, and that would give you your total displacement if you add those together. So that's the first way, and people tend to find that one pretty intuitive. The other one is one that you can probably do and do in your life without... I'm a 5-year-old. And do in your life without realizing you're doing it. So for example, if I told you that like you walk into a store with $60, you walk out of a store with $20, and I should probably get that written on the screen. You walk in with 60 as 10, $60, you walk out with $20, you would probably be able to tell me that that meant that you had spent $40. What you're doing to figure this out is you're saying, okay, well, what did I end up with? $20. What did I start with? $60. The fact that when I subtract those two in that order, it's negative tells me that I spent the money instead of gaining it. You take what you end up with and you subtract what you started with, and that tells you how much it changed from beginning to end. This is a little weird for a lot of people, and like myself included, it's kind of counterintuitive because you are like, okay, well, the beginning goes first. The beginning doesn't go first. The beginning is getting subtracted. There's actually an easier way to arrange the equation, like a conceptually easier way to arrange the equation, which is that if you take what you start with and you add the thing that you do to it, meaning you add the change, that'll give you the thing that you end up with. And we're just taking that equation and subtracting the start from both sides, and that's why it's minus start, or that's a reason to think of why that's minus start. So in this specific case, that means that your displacement is going to be equal to your position minus your initial position. That 0 at the bottom is actually a not symbol, so this is pronounced x naught. These are the variables that the AP exam uses and that are on the AP exam's equation sheet, so I will keep using them. Personally, I would prefer F for final, I for initial, but I think I mentioned this in Unit 0, but this is, I believe, the first time we've seen it in the main unit, so you're going to see this a lot. First off, delta isn't a variable, it's a marker in front of a variable to tell you what to do with a variable, so this is all one thing. You can't divide by delta, you can't to get rid of it, for example. Delta x is one thing. The naught at the bottom of this x is part of the x. It's telling you which x it is. The one without a modifier means the one that is currently just like now. The one with the modifier, and that one can change because if you wait till a different time, you'll have a different x. The thing that's special about x naught is that it's a constant. It's based on the situation. Regardless of how long you wait, it still always started at the same place. So its initial position is there was sort of that fixed value of x naught. So we give it this special thing to denote like, well, this is a constant for the problem. Or this, I guess more so, this is a constant for the situation. So to do that, you put stuff at the bottom right. It's not an exponent. It's not telling you to do math. It's just describing which of the things it is. So one quick thing to note is that total distance traveled, as we've discussed, is a scalar, which means it does not have a sign because it does not have a direction. For us, plus or minus are very much so forward or backwards. Delta x, however, must include a sign. So like for me, I actually explicitly put in the plus sign for any positive vectors. Now, it took a while to build that habit. But I explicitly put in a plus sign for any positive vectors specifically because like it's actually pretty important that it's going forward. It's just as important as if it was going backwards. So being explicit about like, no, this one was forward really can help you remember that it's a vector and that you should be keeping track of that. So if we come back and we do this example now. So we walk forward 20 meters from our room towards the car. Realize I left my glasses on my deck. Walk back 25 meters and then walk 40 meters forward to the car. So before I even do the problem, I want to get a good idea of what's happening in this situation, so I'm going to draw a picture. I think I'm going to do this one on paper. I think that makes sense. So my picture is going to look like starting here, and then we're told, okay, well, we go forward by plus 20. And then we go backwards by minus 25. And then we go forward again by plus 40. A is asking us to find t dt. My t's have little curves at the bottom so that they don't look like plus signs. That's not something I'm going to require you to do, but it's not something that I'm going to stop doing. So just, I guess, get used to that. Wow, the exposure is way down on this thing. And one other weird thing that's going to come up probably pretty soon is that my x's look like this, where I put curves on them, and that's to stop them from looking like multiplication symbols. All right, so these are the things we're looking for. Great. So we have really only one way to find total distance traveled, and that's to just sort of take everything and add it together, not caring about whether or not it's forward or backwards. So in this case, that'll look like plus 20 meters. We then go 25 meters. We don't care that it's backwards. We're just trying to figure out how far we went at all, regardless of direction, and then plus 40 meters. So 20 plus 25 is 45, plus 40 is 85. So we have gone a total of 85 meters. For B, if we're trying to find our displacement, now we care if it was forward or backwards. If you move forward and then move backwards, you undo some of that. If you move backwards and then move forward again, you undo some of that. So I'm going to include the negative if it's backwards and the positive if it's forward, as opposed to just making everything positive. And that'll look like this. We've got 20 minus 25, which gives us negative 5, plus 40, which gives us 35. And again, I'm just going to include the positive sign so that I know that this is 45 meters forward. Total distance traveled doesn't have to include a direction in an answer. Displacement absolutely does, because you need to know where it wound up. It's not enough to just know that it was 35 meters away from where it started. You want to know which direction that 35 meters was in. So hopefully fairly straightforward. Let's move on to average speed and average velocity, which I didn't have a good system for putting in slides previously, so we're going to do it this way. Yeah. So average speed, as we talked about last time, is how you go, what you would need to do to go the same distance in the same amount of time. And so the way that we can find that is that our average speed is going to be equal to our total distance traveled divided by the time that we're traveling for. So just like with how delta x was all one thing, TDT is all one thing. It's not like this is saying time times distance times time. It's saying the total distance that we've traveled. If you prefer to write it as d over t, that's totally fine. For me, I like having the explicit, like, this is the total distance traveled. It's just not just like an arbitrary distance, and it's definitely not displacement. And for me, that makes more sense. Total distance traveled. Which is measured in meters. T is time, which is, for this class, mostly measured in seconds. And you can use any measurements of distance of time for these, but again, just for this class, we're normally going to be using seconds and meters. And speed is meters divided by seconds, or meters each second. Anytime you hear the word each in something's units, it means there's some form of division happening. Great, so that's our equation. The other equation for today is displacement over time, which is our average velocity. I do my V's with a little thing on the end. This is to make them not look like a U. It does occasionally get people to think that they are square roots. They are not. So just, I guess, watch for that. So we talked about this a little bit already, but this is displacement. Which is in meters. And this is still time, which is in seconds. And then we have average velocity, which is in meters per second. And that's pretty much it. I should add, if you don't know the displacement, because displacement is equal to final minus initial position, you could do sort of one setup to do that instead of finding the displacement in different steps. That would be totally fine. All right. So if we come back to that problem that we had previously, Now, if we want to do C and D, just occurred to me that I should have probably talked about how to know which type of displacement you should be using, which displacement equation you should be using. I will circle back to that after we do C and D. So C is what is our average speed, and D is what is our average velocity. And so just going ahead and doing it. Thankfully, we have our equations right there, and we have the stuff we need to use the equations. We actually already figured out total distance traveled and displacement in one. So our speed, we just have to use our A and B. For speed, we just have to use our answer to A, which is, I do like writing out the equation without the stuff plugged in first. So we've got our 85, and then we just needed to divide that by our time, which I didn't put in the problem. Oh my gosh, this is not that I'm a lot better about this now, but should I get the numbers a little better? I do think that past me has made a blunder. All right, sorry about that. So we've got the entire process, and this just got added to the problem. The entire process takes 150 seconds. So I'm going to go ahead and write down over here, probably just next to my picture, that the time for the whole thing is 150 seconds. All right, so that lets us come over here and fill in 150 for our time. If you're being really good about this stuff, you should probably include your units as you go. I kicked the habit of doing that before I ever really developed it because I didn't like how the units wound up looking like variables. I am probably supposed to tell you that you should be writing your units as you go. I tend to emphasize not actually plugging in any of the numbers, which means you don't have the units in it until the very end anyway. So it's not a huge deal as far as I'm concerned, because once you've got the variables solved for, the problem's done, and who even cares what the numbers were? But that is also probably not a particularly good habit. All right, so at this point, we just got to take 85, divide it by 150, and that gives us 0.67, or sorry, 0.57 meters per second. And for our next one, our equation is that we've got displacement over time, which is going to give us our displacement of plus 35 over, sorry, I shouldn't try to do a different color when I'm plugging in. I do not always remember to switch. Over 150. So 35 over 150 gives us 0.23. And I am going to include the positive sign to show that it is 0.23 going forward. I wouldn't mark you wrong if you didn't include it, but also it is a bit more, I wouldn't say it's more correct, but it's certainly does a better job of communicating what's happening to anyone who's looking at your answer. So that's it. If you followed that, you're in pretty good shape. I do want to make sure that we talk about this last bit, which is how to do some slightly fancier algebra with this stuff. And if you're good on this, then you're definitely in great shape. So while sitting in traffic, I figured out that I need to have an average speed of 20 meters per second to make it to an interview that is 400 meters away on time. I drive 15 meters per second for the first 2,000 meters. How fast will I have to drive for the second half to make it there on time? So what's a little bit weird about this is that when you have average speed or average velocity, in general, when you're taking an average, what you're doing is you are Just remembered I needed to describe something, and I'll come back to it. So hopefully I remember. When you're taking an average, what you're doing is you're seeing what uniform value you would need to fit into the rest of it, or to do for the entire thing to yield the same end results by doing it for the same amount of stuff, or with the same amount of stuff. For the averages you're used to, it's with the same like countable, quantized number of things. So if you're saying like, how do we get the, I don't know why marbles is what happened in my head, but here we are, how we get the same, what the average number of marbles per viewer would be. It would be how many marbles would each person have to have so that the total number of marbles is the same once spread across everyone evenly. In that case, the thing you're averaging over is by people, which is a finite, countable, quantized thing. For this, we're averaging over time, and that has some kind of wacky results where you can't just average the speeds if you're going over two fixed distances, because the times for those two things won't be the same. If the time for two legs of a trip are the same, you can average the average speeds of those two and you'll get the average speed of the total because it's averaged over time. Does not work if the distance is the same for the two, unless they are the same average speed, in which case you got lucky, but normally that will not work. If it's not a particularly large difference between the two speeds, you'll get an answer that's very close to correct. But unless you're careful about doing it the right way, you won't get the right answer otherwise. So in particular, for this problem, what we're really going to need to do is think about how these different sections interact with each other, and in turn, how these different sections interact with the total. So I know that for the whole thing, it's going to be 4,000 meters. I also know that for the whole thing, my average speed or average velocity, there's a little less writing for VAV just because I don't write out speed, so I'm going to use velocity for this one, needs to be equal to 20 for the total. So we have a subscript. Which average velocity is it? The total average velocity. I also know something about the first half for A. So for A, the first half, being 2,000 meters, has an average velocity. So I'm actually going to label this as the displacement for the total. I know that my velocity for the first section was effectively 15 meters per second. I also know that my distance for the first section, or displacement for the first section, was 2,000 meters. What I don't know is anything about the second section. Now, you might be able to figure out some pieces of it, but it's not explicitly given in the problem yet. So I don't know my distance for the second section, and I don't know my velocity for the second section. And that's what we're being asked about for A. What's our velocity for the second section? For B, looking ahead a little bit, it's going to be very similar, except for this one, V1 is going to equal 10 instead of 15. And we're going to see how that changes it. All right, so let's do it. So if I'm looking at and this is typically the approach you're going to want to take for these problems, I need to figure out what the question is actually asking me for, which is how fast will I have to drive during the second half to make it there on time. So what I'm being asked for is V2. What are the equations that I know so far that actually involve velocity? Well, we've really only got displacement over time, both of which are going to be for the second section. So if I want to find V2, the first thing I'm going to have to find is the distance for the first section, and then I'm going to have to find the time it takes to do that second section. So this is actually going to be a multi-step problem. So let's look back at the information we have and try to figure out a way to get the second distance. Well, geometrically, it's actually not too bad. I know that the whole thing is 4,000. I know that the first part is 2,000. And I know that if I take the whole thing, that's going to have to equal the two pieces of the whole thing put together. And so if I just want the second part of the thing, all I have to do is subtract the first section from both sides. And if you can look at it and just say, hey, that's 2,000, sure, that's fine, don't worry about it. You do not have to do it this sort of explicitly. But if you get to a harder problem where you can't just immediately do that, it helps to have practiced a more explicit process that will work in most cases. All right, so that tells us that our second part of the trip is 2,000 meters. And what's nice about that is I can pop that up here, and that'll give me my answer if I knew the time, which I don't yet. So next step is going to be, how do we find the time? Well, what if we try a pretty similar approach? The time for the whole thing is going to have to equal the time for the first thing plus the time for the second thing. The only thing that's weird about that is if I look at my givens that I have written down over here, I don't know any of the times. Cool. So I'm going to have to do even more work to figure that out. Well, the only equation I know that uses time so far is still that velocity is equal to displacement over time. If I want to solve for time, I'm going to have to move it to the top, so I'm going to have to multiply each side by time. And then I'm going to have to get rid of velocity, so divide each side by velocity. This equation will come up a lot. It's just rearranging that other one. Time is going to be equal to displacement divided by velocity. And in theory, all of these are average, or if it's a constant velocity, that's fine too. So from here, I can take that equation, and the big reason I didn't plug in the numbers before I solved it was so that I had an equation that I could use time and time again, because I've made no assumptions about the situation other than that I know the average velocity and the displacement. So I can use this for both of my pieces. I can do it with 4,000 and divide that by 20, which will give me did I? No, that's right. Oh, right. Sorry, because it's the time. Which will give me 200 seconds. And I can also do it, and this was using the stuff from the whole thing. So this is our total velocity. And I can also do that with 2,015, which will give us something that is not as easy to just 133. And so what I can now do is I can take these two pieces of information and bring them back over here to this equation to find time 2. Once again, I am going to have to subtract by the time for the first one, which will give me the total time minus time 1. And that'll equal our 200 minus our 133, which will give us out 77 seconds. So I know that my time is 77 seconds for this. And I can take it and bring it up here. And so that'll give us 2,000 over 77, which is 26 meters per second. So again, if you just said, well, the first section was 5 seconds under, the second section has to, or meters per second under, the second section will just be 5 meters per second over, that's actually not quite going to work. Because you're going slower during the first half of the section, it's not actually the first half. It's the first half by distance, but it takes a longer time, so it's not the first half by time. So you actually have even less time left over during the second part distance-wise, so you have to go even faster to compensate in order to bring it up to that value that you wanted of 20. This actually gets much more extreme when we look at B, which I'm going to well, I want you to be able to see all the work over here because we're going to pull from it pretty extensively. For B, let's take a look at things that are different. Well, really the only difference is that first section. My remaining distance is still 2,000, so I don't have to change that. My time is going to be different. So I just need to refigure out what the time for the first part was, which was the distance divided by the time, this velocity. And then I can go back and redo everything that I did with this new information. So if I do that, we've got 2,000 divided by 10, which gives us out 200 seconds as our time for our first section. So if we go ahead and take our equation that we already solved for, which was that our total time minus the time for our first section is going to be equal to our second time, and we plug in our values, we'll get 200 for the total minus 200 for the second time, which tells us that we have 0 seconds left to get there. If I plug this into my equation, I'm going to be dividing by 0, which is telling me that I'm going to need to drive infinitely fast in order to get there on time. What this means is that you can't do it. Basically, you're already late. This is something that if you go to do one of these problems where it's like, travel like this to make the average speed this, if you go through and find out the time that you need to use to get that average speed, and the time you find is either 0, which means that it's exactly out of time, or negative, which means you're already well past the time, then that's telling you that the problem is impossible. You would either need to teleport there instantly or travel backwards in time in order to get the correct average speed, and neither of which is really possible. So that's a thing that can come up. I do want to talk about one last thing, hopefully fairly quickly, which is how can you tell which of these two ways you should be using? People tend to sort of aren't really sure, like, should I be using adding up all the distances or should I be using the final minus the initial? If you have access to that information, like if you know where it starts, you know where it ends, but you also know what happened all the ways in the middle. So like if I tell you, oh yeah, I mean, I started at this tree and I wound up 40 meters in front of the tree after I walked forward by 60 meters and then backward by 20. And you're like, okay, well, what's the displacement? You could either do the final position of 40 minus the initial position of 0, or you could do the plus 60 and the minus 20. And in either case, you would get the right thing. But if I only gave you one of those pieces of information, if I only said I started at the tree, I walked forward by 60, I walked backwards by 20, you wouldn't be able to immediately use this equation because you don't know the start and end location. So if you don't have the start and end location, and specifically if you're also not looking for the start and end location, don't use the equation that has the start and end location. Use the process that has the distances and the signs, because that's what you have. Conversely, if I said I started at this tree, which is 10 meters in front of the origin, and ended 40 meters in front of the origin, you could say, okay, well, I have the final location of plus 40, I have the starting location of plus 10, so the equation that makes sense to use, or the process that makes sense to use, is the one that has those two things. And this is going to be a recurring theme throughout this class. A lot of times you're just going to basically want to say, take the equations that use the stuff we have and include the stuff we're looking for. So, yeah, that's pretty much it. Goodbye, YouTube. Ooh, goodbye, YouTube.